Okay, so from my tech talk today, I'm gonna be speaking about adversarial agents in games. Basically, adversarial agents just means that agents which play against each other or other opponents, such as people and whatever it comes up with. So I'm basically gonna give you an overview of three approaches which are normally used when creating agents for adversarial games. The first one would be the RL, which is reinforcement learning. The second one is rule-based approach, which basically the programmer hard codes the logic for the actual that the agent will follow when playing the game. And the last one is the GNA, which is the generic adversarial networks, which basically tries to mimic the expect players when playing that specific game. So for this one, I'm basically gonna be focusing on the agents which play in board games because board games actually provide a controlled and competitive environment, which is advantageous when you're trying to figure out the properties of this agent. You can actually use it to play multiple games which have their own properties, rules, and play options, including the states of the games in which the player can be in within that game. Normal games like tic-tac-toe obviously have a small state space. You can be in a small amount of possible states on that game compared to others like chess, which basically have a large state space of 10 exponent 43 and go, which is even more larger with 10 to the exponent 100. And the basic fact that with board games, you can actually have a clear outcome at the very end, whether it will be a win, lose, or draw, which makes it pretty much ideal and easy to actually interpret the agents playing. Uh, well, the first overview I'm going to give you is for reinforcement learning. So with reinforcement learning, basically our agent is gonna use action states and rewards. So it's gonna basically when it lands, you're gonna give it a state, it's gonna make an action, then you're gonna punish it or reward it for whatever action it takes there. And hopefully it's gonna basically learn to make the correct moves on playing that game and become even more better than a human as such. Mm, when you're actually training it, you can use multiple options. The first one is that you can use another agent which was trained or a human to actually train it by playing against it, and it will learn playing against that opponent and the rewards to actually be able to play properly. But it might be really hard because you're gonna have to get people or an actual other AI agent to play against it. So most people actually just use self play, which means that you take that agent and you play it against itself, and hopefully it will learn against playing. It will learn when playing against itself whether which is the best decision to make when you are in a certain scenario, and become even more better. There are many different types of agents within the reinforcement learning. Some of you might know Q learning, some even know deep Q learning and the Monte Carlo tree search, which basically have their own advantages and disadvantages when you are actually playing the game or creating an agent for playing that specific game. The implementation. So since neural networks are normally being used these days, you can actually use a neural network to actually create a policy network, which is used by the agent to actually determine the probability of whatever move you will make within a certain state. And you can also use a neural network for evaluating the likelihood of winning when you are in the current position and trying to make a certain move. So we have had like a few reinforcement learning agents that were developed. One is initially trained with human data, then uses reinforcement learning to further its training, like the AlphaGo that play the game Go. And the other version would be a purely self-play training, which basically plays itself from scratch up until it basically learns how to play the game on an expert level. The strengths of reinforcement learning is that it actually uses a exploit and explore rule. So it actually goes through the games playing it. Sometimes it chooses to explore by not choosing an optimal move at a certain stage to see whether it could find another better move. Or it could also exploit it by following a path that's the most optimal to actually strengthen its knowledge about moves from that space. And it actually does work properly because with it actually exploiting exploring, it's able to come up with its own strategies that actually are beyond even human expectations. And it's continuous adapting and playing against itself. It actually improves its own play to suit the environment that it's within and be able to play the game even better than humans. The problems about it is that training it actually takes a lot of resources and time. So it is like extremely hard to basically train in reinforcement learning, especially when you are dealing with games that have a large game state, like for instance, chess and Go. And the fact that it is basically really hard to interpret it, especially when it uses a neural network, because neural networks are basically hard to actually interpret while just looking at their weights. And another defect about it is that if by some reason we actually reach a point where it has never seen within its training, it's probably not gonna win because it has never basically seen it. So it will be completely new to it, and you can exploit that to actually defeat the agent. The second overview will be for rule-based agents. So with rule-based agents, it's basically you are gonna pre-program like the knowledge for the game that you will use, maybe using logical statement or heuristic functions, which basically tell it that if you are in this type of situation, do this. If you are in a certain type of situation, do the other thing. The problem about this one is basically it is being the function is basically being created by a human. So it's only going to be limited by that human's basic potential on knowledge on the game. Like classical methods for this would be the min-max algorithms or the alpha beta pruning. These basic things, methods use an evaluation function. So the evaluation function takes in a state, then uses the properties of that state to determine the game theory value of that state to actually determine whether it will be best if we go through this path to get to that state, which would increase our chances of winning, or should we use another option. So min-max basically just tries to go through all possible moves, and at the end of the depth that it went, it's going to determine the theoretical value of that level and then come back up where it will basically, each agent will choose the best value for itself. So like I said, the three min-max and alpha beta pruning use a game's tree search, which means that from the current position that it's in, it's going to try out different moves to a certain depth, and from that depth it's going to determine the theoretical value that it will be used using the evaluation function that is, well, basically created by a human, and from there it shall use that information to choose the best move for itself. The strength about this thing is that you don't actually need to train it before you actually use it. All you need is just expert knowledge about the game, and then you will be able to create your heuristic function from it, or the evaluation function. And it's highly transparent and easy because you're just using a heuristic function that is initially made by a human. So it is easy to actually look at it and predict why it made this move at this certain point. And the fact that it's actually predictable and reliable because you know that at this certain state, it's going to do this certain move. The problem about it is that, as I said, it is actually based on human experience. So it's never going to actually be better than the human that it created it, unless you just brute force it by actually making the depth that the min max will actually go. Then it might be the person that created it. But from that standpoint, it's kind of iffy. And the lack of flexibility is that since their evaluation function is being hard coded, it cannot actually adapt to like some strategies because it's already like it cannot change or learn. The only way it can actually change is if the the programmer actually goes back and changes the evaluation function himself. But aside from that, it's just gonna stay fixed on the decision making that it's used to. And because of that knowledge, it is pretty hard to actually code it for a game that's mostly complex. Like for instance, Go, because it has like a lot of state. It has a lot of states, which means that even humans cannot like predict every single move or try to actually make an evaluation function that is good enough for the whole game. And the last overview would be the GNA, which is the generative adversarial networks. This networks basically is this agents basically created using two neural networks. The first one is the generator, and the second one is the discriminator. It's this method basically is also used in image creation, where the generator generates a picture and the discriminator tries to tell whether the picture was created by an agent or is a legit picture. So it uses the same logic, but instead it actually looks at the basically game logs of expect players. By using the game logs of expect players, you can actually tell the agent to, given a certain state, is it gonna perform the same moves that the expect did? And the discriminator is gonna try to figure out whether the move that was made was the agent or the expect player. So this basically forms a loop where the generator is given a state, tries to make a move, and make that move as similar to the expect player as possible, while the discriminator tries to distinguish whether this move was made by a agent or the actual expect. So this is actually trying to, at the goal of this thing is basically to try to actually mimic human behavior within the game. So this will actually try to mimic the moves of the expect player while playing that certain game. And like like the rule based, obviously it's not gonna play better as like the better than the expect because it's trying to actually mimic that expect, and it's gonna have all the flaws that the expect have while playing that certain games. So if the expect is actually making a wrong move but he doesn't actually know it in each and every game, the agent will also make that same correct move because it's mimicking him. Okay, so yeah, I did go to the discriminator. So the strength of this is that since it's actually mimicking the human behavior, it's quite useful in creating like personalized and realistic training opponents. Because when you play it, you're gonna feel like you're playing against a normal person and not just a machine. So it could be useful when you're trying to learn a new game and playing against that person, or creating a game that has different levels of expertise, like beginner, intermediate, and expert, where you can make different agents for each of those levels using the mimicking beginners, intermediate, and experts. Okay, and the challenges of it is that, as I say, it's gonna need a lot of data from experts. So you're gonna have to record a lot of data from expert players, which is gonna be hard for you to actually find. And the fact that you are actually having two neural networks which are looping, with the generator creating a move and the discriminator trying to see whether it's a agent or the expert. Training it can have like stability issues, which is kind of a challenge for us. And the last thing is that it's obviously limited to that expert player's knowledge. So if they make the same mistake, then it's gonna make that mistake. So this is basically just a summary of what I said. And choosing the right method is gonna determine by you and what game you're gonna actually wanna be creating, or what your resources available are. If basically you have a lot of resources and you're trying to make the most optimal agent, I suggest that you use reinforcement learning. If you are looking for a more simpler game, if you are trying to create an agent for a more simpler game, or just basically trying to study games, well-studied games that are pretty known, then you can just use the rule-based one because you have a lot of information about it. And when you are actually trying to teach people how to play the certain game against other people, so you might actually want to use the GNA, which will mimic a person's behavior, so they will feel like they're playing another person, which could be educational, and they would learn how to play against human opponents. You have the real world applications. You have, for reinforcement learning, we have AlphaZero. For the rule base, we have the Stockfish. And for the GNA, it's basically just educational training bots. And the practical recommendations is that they while evaluating the actual game and scope of it, you must actually choose the agent based on how complex or big the game state is. If basically the game is quite large, then a rule base would not work for you because you have to actually have a professional to actually like understand all the moves within the game to actually make an agent that's able to play the to make the best move in each scenario that they can come up with, which would be pretty hard if you look at agents that are like Go, which have like a lot of states, and you have about 250 different moves on average at each stage. And based on the goals that you actually would want to make for the game, if you are looking for optimal performance, I suggest that you actually go with reinforcement learning. When you are looking for transparency, then the rule based would be okay for you because you can interpret it well because it uses a heuristic function. And if you are looking for more human-like interactions, then I said just the GNA for you. You can also create hybrid approaches to leverage the strengths of multiple methods, like the Stockfish, which sometimes actually uses a neural network along with a alpha beta pruning to determine what move it should make. So the conclusion is that each method has its own unique strengths and challenges, and technically there's no universal solutions for all the games. So it depends on you what you actually wanna create and the game that you wanna create it for to actually choose what approach you're gonna use. And that would be the end of my presentation.